Have you seen this series? The three-body problem is one of the biggest challenges in physics. It shows how it's almost impossible to predict the exact movement of three objects pulling each other with gravity. The math goes wild, and everything turns into chaos. Now imagine a planet orbiting not one, not two, but three stars. A place where the sky can have up to three suns shining at the same time, changing the climate, the light, and the tides in unpredictable ways. Triple star systems are more common than you might think in the Milky Way. A real example is the HD, 399 system, where a planet orbits three suns that dance around each other in a complex gravitational ballet. In this video, we'll dive into this strange universe and find out what happens when life has to adapt to a sky with three suns, and why this changes everything we know about where life can exist. If you think the universe is simple, triple star systems are here to prove otherwise. They are like a cosmic dance that seems like ballet. But instead of rehearsed steps, we have almost constant chaos. In our solar system, everything revolves around a single star, the Sun. Gravity acts predictably, and we can precisely calculate the planet's movements. But when you add a second star, it already becomes hard to predict stable orbits. And with three, it turns into a mathematical puzzle with no exact solution. This happens because each body exerts a force on the others, and these forces constantly change, causing complex and often unpredictable motions. That's why the three-body problem doesn't have a closed-form formula, but rather an infinite range of possible behaviors. Despite the chaos predicted by the equations, the universe manages to keep these systems relatively stable, at least for millions or billions of years. Astronomers have identified two main types of triple systems. One is hierarchical, where two stars are very close to each other, and the third is far away, orbiting the pair. This creates greater stability because the influence of the distant star is gentler. The other is close triple systems, where the three stars are relatively near each other and their orbits cross. These are the most chaotic and hardest to understand. Now, imagine a planet trying to survive in this tangled web of forces. The scenario could be terrifying for any form of life. The sunlight changes erratically, with up to three suns appearing in different positions in the sky, causing extreme temperature variations. But this also creates unique opportunities. The presence of multiple stars can actually extend the habitable zone, the range where liquid water can exist, because the planet receives energy from different sources at different times. One of the most studied systems is HD 131399, discovered recently, which has a primary star and two companions. The planet's orbit in this system is so complex, it can go through periods of relative stability and then major turbulence, almost like living a cycle of chaos and calm. Another fascinating example is the Alpha Centauri system, the closest to our Sun. It's a triple system with two main stars close together, Alpha Centauri A and B, and a red dwarf called Proxima Centauri, which has a potentially habitable planet. With so much instability and drastic environmental changes, life, as we know it, would face enormous challenges. But astrobiology reminds us that life is resilient and adaptable. On worlds with three suns, evolution might take different paths, perhaps with biological cycles linked to the complex movement of the suns, or special adaptations to handle the variations in light and temperature. The three-body problem deals with understanding how three objects in space, all with mass and subject to gravity, move and interact with each other over time. It sounds simple, but it's a puzzle with no general exact solution. To grasp the problem, let's start with the basics. Two bodies. If you have two objects, like the Sun and the Earth, Newton's physics allows us to calculate their orbits precisely. Earth revolves around the Sun following a well-defined elliptical path, and this orbit can be predicted accurately for thousands of years. That's because the system is relatively simple, just two masses, each exerting gravitational force on the other. But what if we add a third body? It could be the Moon, another planet, or a nearby star. With three objects, gravitational interactions become much more complex. Each body feels the force of the other two, and all are moving simultaneously. This system stops being simple and turns into mathematical chaos, where tiny changes in initial positions can cause massive differences in future trajectories. This is the essence of chaotic dynamics, a field that emerged precisely to deal with this kind of unpredictable behavior. The three-body problem has been so challenging that since the 17th century, when Isaac Newton formulated his laws of gravity, mathematicians have been intrigued by it. To this day, there's no single formula that can describe the motion of three bodies with absolute precision over all future time. Instead, there are approximate solutions and numerical methods that simulate the movements in tiny steps, computing the force each body exerts on the others and updating their positions accordingly. These simulations require supercomputers and advanced algorithms because the system is too sensitive to even the smallest imprecision. That's why predictions are only reliable for limited periods. Beyond that, the system can evolve in unexpected ways, and calculated trajectories become useless. But why does this matter so much? The universe is full of systems with multiple bodies, binary or triple star systems, planetary systems with several moons, star clusters, entire galaxies. Understanding how these bodies interact is fundamental to knowing how the cosmos evolves, how planets form, and how stars and black holes collide. A fascinating example is triple star systems. Despite the potential for chaos, some of these systems maintain surprising stability for millions of years. This happens thanks to specific orbits that avoid violent collisions. But not all are so lucky. Many triple systems are unstable, and one of the bodies can be ejected from the system, flung into space at high speed. These runaway stars travel alone, far from any galaxy, and studying them helps us understand galaxy dynamics and matter distribution in the universe. Beyond stars, the three-body problem is crucial to understanding planetary stability. In either systems with more than one sun, called binary or multiple systems, planetary orbits can be disturbed to the point of becoming erratic. This can result in a planet being ejected from the system, colliding with a star, or entering an eccentric orbit that causes severe climate changes, potentially affecting the planet's habitability. And that's one reason why the three-body problem is so relevant in the search for life beyond Earth. For a planet to host life, it needs relatively stable conditions for millions or billions of years, including an orbit that maintains temperatures compatible with liquid water. If the orbit is unstable, life will struggle to evolve or even survive. In the 20th century, the three-body problem opened the door to chaos theory. The work of mathematician Henri Poincaré showed that even systems governed by deterministic laws, like gravity, can behave unpredictably over the long term. This revolutionized scientific thinking because it showed the universe can be both orderly and chaotic, depending on the scale and system studied. In the modern era, with advances in computing, scientists can simulate multi-body systems in great detail using numerical integration techniques like Runge-Kutta and adaptive methods that balance precision and computational cost. These simulations are used in space missions to plan probe trajectories, predict asteroid encounters with Earth, and study complex star systems. Another field where the three-body problem has direct impact is gravitational wave research. First, detected in 2015, collisions of black holes and neutron stars involve multiple massive bodies in orbit, and accurate models of these interactions are essential to interpret the signals captured by detectors like LIGO and Virgo. Finally, the three-body problem is a bridge between physics, astronomy, mathematics, technology, and even philosophy. It reminds us that even knowing the fundamental laws of nature, predicting the future can be impossible in certain systems, revealing the beauty and complexity of the cosmos in all its depth. Now imagine expanding the problem to 4, 5, or even hundreds of bodies, as happens in complex planetary systems, star clusters, or even galaxies. Each additional body multiplies the complexity of the system almost exponentially, creating a web of gravitational forces that intertwine and constantly influence each other. In this context, the concept of gravitational chaos becomes even more important. Small variations in initial conditions can drastically change the evolution of the system. For example, a planet in a system with multiple stars might appear stable for millions of years, but an apparently insignificant event, such as the passage of a comet or a disturbance caused by a neighboring star, can trigger a series of chaotic interactions that lead to the planet's ejection or even collisions between bodies. In our own solar system, although it is relatively stable, multiple gravitational interactions have already been identified. The orbital resonance between Jupiter and Saturn, for example, creates dynamic patterns that influence the orbits of asteroids in the main belt and may even have caused mass extinctions on Earth by altering the flow of comets into the inner system. Furthermore, the presence of rogue planets, bodies that wander the galaxy without being bound to any star, adds an extra layer of mystery. These planets, often ejected from their original systems by complex gravitational interactions, can cross solar systems and cause temporary disturbances. Detecting these planets is a huge challenge, as they do not emit their own light, but their gravitational influence can be perceived through the movement of nearby stars or gravitational microlensing. Recent advances in space telescopes and ultra-precise measuring instruments have allowed astronomers to identify candidates for these rogue objects. Each new discovery helps expand our understanding of planetary formation and evolution and the dynamic processes that shape the galaxy. Another fascinating aspect is the advanced computer simulations that, through numerical models, allow predictions of scenarios where multiple bodies interact over thousands or millions of years. These simulations not only aid scientific understanding, but are essential for planning space missions, such as sending probes to binary systems, studying exoplanets in complex orbits, or even understanding possible cosmic collision risks with Earth. But what about planets orbiting triple star systems? How do they manage to survive this chaotic dance between three suns? Well, the answer is, with great difficulty, and a lot of luck. In these systems, gravity doesn't come from just one star, but from three bodies constantly moving, creating highly unstable orbits. Many planets get thrown out of the system, while others fall into trajectories that lead them to be swallowed by one of the stars. However, there are regions called stable zones, where the gravity of the three stars combines in a way that allows a planet to maintain a relatively safe orbit for millions of years. A notable example is the HD 188753 system, where a giant gas planet was detected orbiting one of the stars, while the other two form a close binary pair. The gravitational complexity there challenges traditional planet formation models, showing that nature can create solutions far more ingenious than we imagined. Another system that draws huge interest is Alpha Centauri, which is actually a triple system, with Proxima Centauri, the red dwarf, hosting a potentially habitable planet. The gravitational interactions between the stars create a dynamic where the planet faces drastic variations in radiation received and the forces shaping its orbit. The existence of these planets in triple systems raises fundamental questions about the possibility of life. How do extreme radiation and gravitational forces affect the atmosphere and climate? What adaptations would be necessary for any form of life to survive there? Moreover, these systems are a natural laboratory for studying the three-body problem, since the planetary and stellar dynamics are among the most complex and fascinating examples of gravitational physics. Triple systems force us to expand our concept of what is possible in terms of orbital stability, planetary evolution, and even the very definition of the habitable zone. They invite us to rethink life in the cosmos, showing that the diversity of environments is far greater and more complex than the traditional view centered on simple solar systems. But let's imagine something even more radical. What if a third star, an extra sun, entered our solar system? What would life be like with three suns? First, the mere arrival of a new star would completely change the orbits of the planets we know. The extra gravity could destabilize Earth and its neighbors, turning what is today a relatively stable system into a chaotic and unpredictable dance. What would happen to Earth? Would we survive? If the new star settled into a stable orbit far enough away, it's possible Earth could keep existing at least for a while. The habitable zone of our system would change drastically, with a combination of light and heat coming from 2 or even 3 sources, profoundly altering climate and seasons. Imagine double or even triple sunrises painting the skies in unknown ways. Days and nights would be very different, perhaps with periods of continuous light interrupted by brief nights, like on planets with unusual orbits. But the most serious consequence would be long-term gravitational instability. Small variations in orbits could eventually send planets into elliptical paths, or even eject them from the system. With a third sun, Earth's tides would be stronger and more irregular, affecting oceans, tectonics, and possibly life itself. Still, life's resilience, which has survived giant impacts, ice ages, and mass extinctions, suggests we might adapt for a time to these extreme changes, although the planet and its biosphere would certainly be transformed forever. This speculation helps illustrate the challenge of triple systems, how life can arise and persist amid the gravitational and energetic complexity of three suns, which alter not only orbits, but the very idea of home for any planet. If you enjoyed this deep dive into the chaos of triple star systems, don't forget to hit like, subscribe, and ring the bell so you won't miss any videos. See you next time.